Somewhere past the edge of everything you've ever known, a wall of material is quietly building up, pressing inward from the darkness between the stars, and the only reason anyone on Earth knows about it at all is because a 48-year-old spacecraft has spent the last several years accidentally measuring it happening in real time. In 2024 and 2025, scientists went back through years of fresh data being sent home by NASA's Voyager 2, layering it against new readings from its twin, Voyager 1, and what they found wasn't a single dramatic headline moment. It was something slower, stranger, and honestly more unsettling. Proof that the density of the material surrounding our entire solar system has been steadily climbing for years, with no clear sign of where it stops or what it means for the region of space our sun is currently drifting through. Scientists studying this data have used a comparison that should stick with you long after this video ends. They've compared what's happening out there to snow piling up in front of a snowplow. This is that story, told using real, published, peer-reviewed data, and by the end of it, you'll understand exactly why the researchers who found this still don't fully know what happens next. To understand why this discovery matters, and why it's genuinely unsettling once you understand the physics behind it, you first have to understand exactly where Voyager 2 is and how it got there. Voyager 2 launched from Cape Canaveral on August 20th, 1977, one of two identical spacecraft sent out to take advantage of a rare alignment of the outer planets that occurs only once every 175 years. It remains, to this day, the only spacecraft in human history to have visited all four giant planets, Jupiter, Saturn, Uranus, and Neptune, up close in a single continuous mission. After its planetary tour ended in 1989, Voyager 2 kept traveling outward, eventually crossing the heliopause, the true boundary separating our solar system from interstellar space, on November 5th, 2018, 6 years after its twin, Voyager 1, made the same crossing through a completely different region of the boundary. Both spacecraft are now traveling through what scientists call the very local interstellar medium, the region of space immediately surrounding our solar system, still close enough, in cosmic terms, to feel the lingering influence of our sun, but fully outside the protective bubble that has shielded our entire solar system for 4.5 billion years. Here's the part almost nobody outside a physics department actually knows. Even though Voyager 1 and Voyager 2 have technically left the solar system, they haven't stopped sending back genuinely important data. On board both spacecraft sits an aging but still functional instrument called the Plasma Wave Science System, designed decades ago at the University of Iowa, capable of detecting electron plasma oscillations, natural, physically triggered ringing frequencies produced when the surrounding interstellar gas gets disturbed. Every time a violent eruption on the surface of our sun, called a coronal mass ejection, sends a shock wave rippling outward through the solar system and eventually slamming into the interstellar plasma beyond the heliopause, both spacecraft can detect the resulting oscillation and use its frequency to calculate exactly how dense the surrounding material actually is at that precise moment. It's essentially a way of remotely weighing the emptiness of interstellar space, using the ringing tone produced whenever something disturbs it. And when scientists began compiling years of these measurements together, from Voyager 1's readings all the way out past 160 astronomical units, and Voyager 2's readings from its own separate trajectory, a clear, consistent, and frankly startling pattern emerged. One that took shape gradually across years of painstaking, cross-checked analysis rather than arriving all at once in a single dramatic data set. The density wasn't staying flat. It wasn't fluctuating randomly around some stable average, the way most scientists originally expected once both spacecraft finally crossed into true interstellar space. It was rising, steadily, consistently. Voyager 1's electron density measurements, published in a January 2024 paper in the astrophysical journal Letters, showed the surrounding plasma density had been generally climbing since the spacecraft's initial heliopause crossing back in 2012, all the way out to its most recent measurements past 160 astronomical units, roughly 15 billion miles from the Sun. Following a major pressure pulse detected around 149 astronomical units in 2020, the density appeared to level off, holding at approximately 0.147 electrons per cubic centimeter based on the most recent 2023 measurements, a level scientists believe may represent Voyager 1 finally reaching a broad density peak, or possibly, unsettlingly, an entirely new physical regime nobody fully understands yet. Voyager 2, sampling a completely different independent region of the boundary, found the same fundamental story unfolding. Its own plasma wave measurements, tracking a rising density gradient from its earliest interstellar detections in 2019 through more recent readings collected years later, match the same overall upward trend Voyager 1 had already revealed, despite the two spacecraft traveling in almost entirely different directions through space, separated by vast distances and years of independent observation. Two machines, two different trajectories. Two independent confirmations of the exact same unsettling trend. The deeper both spacecraft travel into interstellar space, the denser the material around them appears to become. Here's where the story gets genuinely strange, because scientists don't fully understand why this is happening, or more importantly, when or if it will stop. Researchers working on this data, including physicist Don Gurnett, one of the lead scientists behind the Voyager plasma wave instruments before his passing, offered an explanation using a comparison that has stuck with nearly everyone who's heard it since. According to current models, our entire solar system as it drifts through the galaxy may currently be approaching, or possibly already pushing into, a genuinely denser pocket of interstellar material that gets compressed and effectively piles up directly in front of our solar system's leading edge as we move through it, in almost exactly the same way that snow piles up in front of a moving snowplow, compacting into a denser and denser wall the farther the plow pushes forward. Current kinetic models referenced in ongoing research suggest this density buildup may reach its peak somewhere between 200 and 250 astronomical units from the Sun, a threshold neither Voyager spacecraft has fully reached yet, meaning both machines are, right now, tonight, still climbing directly into the thickest part of whatever this structure actually is. Sit with that for a second, because it's worth actually understanding what it implies, and it's worth doing so slowly because the physics here rewards patience far more than panic. Our Sun isn't sitting still in the galaxy. It's moving, dragging our entire solar system, and the protective heliosphere bubble surrounding it, through the interstellar medium at roughly 45,000 miles an hour. Plowing Zur material happens to occupy the space directly ahead of us. For most of scientific history, researchers assumed the interstellar medium immediately surrounding our solar system was relatively uniform, a thin, mostly consistent haze of gas and dust. Voyager's data now strongly suggests otherwise. We appear to be approaching, or already inside the leading edge of, a region where that material is measurably thicker, denser, and more compressed than the space our solar system has been passing through for a very long time, and neither spacecraft, nor any model built from their data so far, can yet say with confidence exactly how much denser it eventually gets, or what happens to our solar system's protective bubble once we're fully inside it. And this isn't a purely theoretical concern floating somewhere out past the edge of relevance to life on Earth. In February 2025, a separate team of astronomers published new findings, unrelated to Voyager directly but deeply connected to the same underlying story, revealing that our entire solar system had physically passed directly through the Orion star-forming complex, a massive structure connected to something called the Radcliffe Wave, a giant wave-shaped chain of gas and newborn stars stretching across a significant portion of our galactic neighborhood, roughly 14 million years ago. That means this isn't the first time our solar system has plowed directly through a denser region of galactic material, and it almost certainly won't be the last. Voyager's current readings may be giving humanity its first direct, in-place measurement of exactly this kind of encounter happening again, in real time, using two aging spacecraft that just happened to be in exactly the right place, decades ahead of when scientists could have ever built a purpose-made mission to measure it on purpose. So why should any of this genuinely concern you beyond simple scientific curiosity? Because the heliosphere, the bubble of solar wind surrounding our entire solar system, is not just an abstract diagram in a physics textbook. It is the primary reason Earth, and every other planet in our solar system, isn't constantly bombarded at full intensity by galactic cosmic rays, the extremely high energy particles produced by distant supernova and feeding black holes scattered throughout the galaxy. The strength and size of that protective bubble is directly determined by the balance of pressure between the outward push of our sun's solar wind and the inward pressure of the surrounding interstellar medium. If Voyager's data is correctly indicating that the interstellar medium immediately ahead of us is becoming measurably denser, that inward pressure increases, and basic physics suggests the heliosphere itself could, over time, shrink in response, compressing tighter around our sun and planets than it has been throughout most of recorded human history. A smaller, more compressed heliosphere means less shielding, and potentially higher levels of galactic cosmic radiation eventually reaching the inner solar system, including Earth. Over timescales, scientists are still actively working to calculate and fully understand. To be absolutely clear here, because responsible reporting on real science requires it, nobody is suggesting Earth faces any kind of sudden, immediate danger from this. These density changes and any resulting compression of the heliosphere are believed to unfold over scales of centuries, possibly millennia, not years or decades, and Earth's own atmosphere and magnetic field provide substantial additional protection against cosmic radiation entirely separate from the heliosphere itself. Still, some researchers point out that even a modest, gradual increase in the level of galactic cosmic radiation reaching the inner solar system could have measurable, cumulative effects over long stretches of time, on everything from the reliability of satellite electronics to the total radiation dose absorbed during long-duration crewed missions, beyond Earth's immediate protection, the kind of effects that wouldn't matter much year to year, but could matter considerably added up across generations. This is not a story about an imminent catastrophe. It's something quieter and, in its own way, more genuinely unsettling. Proof that the protective bubble surrounding our entire solar system, the one shielding every planet, every moon, every living thing that has ever existed, is not a fixed, permanent structure. It responds dynamically to the changing environment of the galaxy around it, and thanks to two accidental messengers built in the 1970s, we are, for the first time in human history, actually watching that response begin to unfold, measured directly in real data rather than modeled purely from theory. Recent analysis published in 2025 and 2026 has only added more layers to this picture and more reasons for scientists to keep watching closely. Researchers, tracking both spacecraft through what's now called the outer heliosheath, the turbulent transition region just beyond the heliopause, have documented multiple additional pressure fronts and shock events slamming through the region since the original 2018 and 2012 crossings. Some driven by solar activity, others potentially connected to the broader structure of the interstellar material itself. Voyager 1 now passed 172 astronomical units from the Sun, and Voyager 2, trailing behind at roughly 143 astronomical units, continue registering these disturbances as they travel, each one adding another data point to models, attempting to map out exactly how far this density buildup extends and exactly where, if anywhere, it finally begins to level off. According to the most recent kinetic models referenced in this ongoing research, both spacecraft are still climbing toward that predicted density maximum, near 200 to 250 astronomical units, meaning the most significant, most revealing measurements in this entire story may still be years away from actually happening, assuming either spacecraft's power supply holds out long enough to record them. Here's the part of this story that tends to catch people off guard once they actually think it through. Cosmic radiation isn't just an abstract concern for planets sitting quietly in their orbits. It's an active, immediate engineering problem for every single satellite currently orbiting Earth, and for any future astronaut attempting a mission beyond low Earth orbit. NASA's own radiation modeling for deep space missions, including plans for future crewed trips to Mars, already factors in the current strength and shape of the heliosphere as a baseline level of protection astronauts can expect to rely on. If Voyager's data is correctly signaling that this protective bubble is beginning to respond to a denser surrounding environment, even gradually, even over long timescales, it directly affects how mission planners need to think about radiation shielding requirements for spacecraft, satellites, and future long-duration space habitats, decades before any of those changes would ever become noticeable here on Earth's own surface. There's an added layer of urgency buried inside all of this that researchers are quietly aware of too. Both Voyager spacecraft are running out of power. Their radioisotope thermoelectric generators, fueled by a steadily decaying block of plutonium, lose a small measurable amount of usable energy every single year, a decline that has already forced NASA engineers to permanently shut down several onboard instruments on each spacecraft just to keep the remaining, most essential systems alive. Current projections from the mission team suggest both Voyager's scientific instruments, including the plasma wave systems responsible for every density measurement described here, will likely run out of usable power sometime between 2025 and 2030. That means humanity has an extremely narrow closing window of time in which these two specific spacecraft can continue directly measuring whatever this rising density structure actually is, before the only two eyewitnesses we currently have anywhere near the edge of our solar system go permanently silent, potentially years or decades before scientists fully understand what they've been describing. NASA is aware of exactly how limited this window has become, which is part of why a mission concept called Interstellar Probe has been seriously discussed within the heliophysics community, a dedicated spacecraft purpose-built to travel beyond the heliosphere, carrying far more advanced instruments than either aging Voyager launched with, potentially able to look back at our solar system's protective bubble from the outside and directly measure its true size and shape for the first time. However, that proposed mission was notably not recommended as a priority in the most recent Decadal Survey for Heliophysics Research, released in 2024, a decision that has genuinely worried some scientists in the field who fear humanity may lose its last direct connection to this region of space for years, or possibly decades, right at the exact moment the data is becoming most important to understand. It also helps to understand exactly how remarkable it is that this data exists at all, given what these two spacecraft were originally built to do. Neither Voyager 1 nor Voyager 2 was ever designed with interstellar plasma density in mind. Their instruments were built in the 1970s, specifically to study the planets, the intense radiation belts around Jupiter, the icy rings of Saturn, the strange tilted magnetic field of Uranus, the storms of Neptune. The Voyager Interstellar mission, the extended phase of the program tasked with actually studying the boundary of the solar system and the space beyond it, wasn't even formally established until after both spacecraft had already finished their planetary tours in 1989, essentially repurposing hardware nobody originally built for this exact job. Every single density measurement, every plasma oscillation event, every piece of data behind this entire story is being pulled from instruments, engineers in the Nixon and Ford administrations, designed for a completely different mission, decades before anyone could have predicted these same machines would still be operating and still making headline-worthy discoveries well into the 2020s. Consider for a moment what it actually means that this entire discovery rests on two machines that predate the invention of the personal computer, the compact disc and the modern internet, still transmitting usable scientific data across a gap so vast that a single radio signal traveling at the literal speed of light takes over 18 hours just to arrive. Every single density measurement described in this video came from spacecraft running on computer systems with less processing power than a basic pocket calculator, using instruments engineers in the 1970s built to study our own solar wind, never imagining those same instruments would one day be humanity's only direct window into a genuinely mysterious, potentially significant shift happening in the space immediately surrounding our entire solar system. It's worth stepping back too and considering the mission engineers themselves, the people who actually keep this fragile, decades-old operation running day to day. Many of the scientists currently overseeing Voyager 1 and Voyager 2 have spent their entire careers on this single mission, some inheriting responsibility for the spacecraft from mentors who worked on the original 1977 launch and have since retired or passed away. Suzanne Dodd, the mission's current project manager at NASA's Jet Propulsion Laboratory, has described the day-to-day reality of running Voyager as an ongoing negotiation with an aging, increasingly fragile machine, one where every command sent has to account for outdated systems, thinning power margins, and instruments never designed to still be operating this deep into the 21st century. Every fresh data point in this density story represents not just raw physics, but an active, ongoing act of careful engineering stewardship, keeping two of humanity's oldest functioning spacecraft alive just long enough to keep answering questions nobody even knew to ask when they first launched. So when someone tells you that NASA reanalyzed Voyager 2's deep space data and the results are terrifying, understand exactly what that really means. Because the honest version of this story is stranger and more quietly important than any single dramatic headline could fully capture. It doesn't mean an immediate threat is racing toward Earth. It means something slower and more fundamental. Real, measured, independently confirmed evidence that the protective bubble surrounding our entire solar system may currently be pushing into a denser region of the galaxy than it has passed through in a very long time, an unfolding event scientists are only now able to directly observe in real time, using two failing, decades-old machines that happen to be in exactly the right place, at exactly the right moment in cosmic history, before their own power finally runs out for good. There's also historical precedent worth understanding here. Because our solar system's journey through denser and thinner regions of the galaxy isn't a new phenomenon, even if directly measuring one in progress is. Astronomers studying the galaxy's structure have long known that the Sun, along with the rest of our solar system, orbits the center of the Milky Way roughly once every 230 million years, drifting through wildly different neighborhoods of gas, dust, and stellar material along the way, some sparse and nearly empty, others considerably denser and more turbulent. The 2025 discovery connecting our solar system's path to the Orion Complex and the Radcliffe Wave strongly suggests these encounters happen on a semi-regular basis across geological timescales, meaning the very local interstellar medium isn't a fixed, static environment at all, but a shifting, textured landscape our entire solar system has been passing through, largely unnoticed for billions of years. Voyager's data may simply be catching humanity's first direct, close-up glimpse of exactly this kind of transition beginning to unfold, using two machines that happen to launch at precisely the right moment in an almost unimaginably long cosmic timeline. Voyager 2 is still out there tonight, still transmitting, still adding one more data point to a mystery scientists have only just begun to understand, racing against its own dwindling power supply to send home as much of this story as it possibly can before going silent forever. If two failing 50-year-old spacecraft can still uncover something this significant about the space surrounding our entire solar system, imagine what else is quietly waiting out there to be discovered before it's too late to find it. Every year, these two machines keep transmitting as another year of direct, physical evidence about a process no textbook fully predicted, gathered from a place no future mission may be able to reach again for a very long time. Subscribe now so you never miss the next real discovery from the edge of the universe.